Okay, so I think we can probably get started. I see the number how they increase it now, so asymptotically with there, I think. Okay, so welcome everybody. We have again a topical meeting. This time we have a big topic, so we have invited Wouter Verkerke, so you know very well probably most of you, as one of the main authors of RooFit. So he will be discussing development of the parallelization ahead going on NICA. And then a second presentation, we have a command line interface tool from Schreiner. So the reason for having this completely different topic here is because actually RooFit or the related software could be customers for this tool. So it makes sense to present it to a wider audience. Okay, so Wouter, I see you actually broadcasting your slides?
Yes, I thought that would perhaps be the easiest.
No problem. I confirm we see that, so please go ahead. Thank you.
Okay, thank you, Eduardo. So, yes, so I will show you a few things about work that has been going on RooFit parallelization. This talk is fairly down to earth. I start with a very brief introduction. And I apologize for all the text on the slide. I will not mention everything. So I think all of you know what RooFit is. In my mind, I think the way I usually think about it, it's an object-oriented language to write probability models, and then once you have such a model expressed as a function, tree of function objects, you can fit these things, make plots, do toy event generation, and I think one of the nice features is that it's been shown to scale to very complex models. Typical Higgs combinations, they have more than 10,000 objects. So the goal is, and this is not really about parallelization but optimization, but these things often go hand in hand, is that there is quite a bit of computational optimization in there, efficient toy generation, analytical integrals for probability densities wherever possible, general techniques like caching and lazy evaluation of expensive objects, identification of constant terms, and for a typical PDF, this makes a difference, speed up factor 2 to 20. So the philosophy I have here is that the idea is that users should concentrate on formulating the physics problem, and the RooFit code will worry about computational optimization under the hood. The only part where users interact directly with possible optimizations is if there are analytical integrals they know about, or they have efficient algorithms to generate particular PDFs. Now for parallelization, I would like to follow a similar philosophy so that people can do a parallel calculation of a likelihood without really having to deal with all of the underlying problems. Now when thinking about parallelization in RooFit, it's good to think for a moment how users use RooFit and where parallelization could be beneficial. In general, RooFit is an ingredient of sort of the semi-interactive final step of the physics analysis. So that means that people run fits, they make plots, they extract their final results, and if you look at a typical workflow, this is close to interactive. So ideally, whatever you do should take a few seconds to a few minutes, but not 1 or 2 hours, because then you're not really doing interactive work anymore. Now, if you have a simple to moderately complex model, anything you can write down in 10 to 15 lines of code, this interactive speed is almost always there. It mostly goes wrong when you try to be very ambitious. Here is a couple of examples. You can build a super complex likelihood model, like for example the Atlaser CMS Higgs combination, where you fit 200 data sets to 1,000 parameters, and then it can easily take more than an hour. Another very different way in which you can be ambitious is if you have unbinned maximum likelihood fits with very large data samples. So typically if you have multidimensional observable space with complex multidimensional PDFs, unbinned likelihood fit makes sense, and this can take a long time simply because you will have millions of events. Another way in which you can be slow is if you need Monte Carlo style numerical integrals. So if you try to do other types of ambitious things like what I would call time-dependent angular analysis of Dali's decay. So this means you really have a very high dimensional observable space with very non-trivial correlations between them. one sometimes needs Monte Carlo integrals to be able to calculate the normalizations of these PDFs, and this can also slow things down. Lastly, if you do, for example, Lyman constructions of confidence belts, if you're outside the regime of asymptotic statistics, this is also a case where you can spend a lot of CPU because you need to do many fits to toy data samples. So what I aim to focus on is actually the first 3 use cases. Number 4, the construction of these confidence belts. This is somehow inherently easily parallelizable by end users by just submitting a few thousand jobs to a batch system and then let each job calculate 1 or more points for such a confidence belt. So I don't think we need to focus on that right away. In the spirit of the semi-interactive use, what I would like to aim for is sort of a factor 10 to 30 speed up for someone who has a large multi-core machine, so that you can reduce something that would take a few hours, which is clearly non-interactive, to a few minutes, which is again in the regime of interactive analysis. So parallelization is already there in RooFit in some simple form. Let me just explain to you how that works. I mean, in principle, it's all super easy. A likelihood based on is effectively evaluating the log of the PDF for any event. So this is inherently repetitive, so it's easy to parallelize because it's a lot of calculations that are of the same type. So the strategy that RooFit has is that it will divide the data in n equally sized chunks, and then each of those chunks they get calculated by a slave process. I made a little diagram here which illustrates that, and they each do 1/n of the work. So as I said, it's all done in a relatively rudimentary way. So there's no multi-threading, it's really just multi-process. I use fork. Inter-process communication is some clever combination of pipes and shared memory that was implemented by someone else for me. Originally it was just pipes. And the sequence of operation during a fit is really quite simple. So there is a master process which runs meanly and drives the whole minimization process, and whenever a new evaluation of the likelihood is needed, the master process sends to each of the slaves a calculate request for 1/n of the likelihood. These calls they don't block. Then the retrieve request for all of these they block, so that means that all of the retrieves only return when each of the calculations are done, and in principle they should be all done at the same time. Then I just mention it for completeness, if there is a flag also sent that there were evaluation errors, there are more details available on what went wrong in the slave processes, and those are then retrieved at that point. This usually doesn't happen. Then there is also a combined, so for a likelihood this just means adding the partial results. This is fed to MinV. MinV decides that it has a new point in the parameter space it wishes to sample. So those new parameter values are sent to all of the slaves, and then you just go on and iterate this. Just to quantify how it works, the amount of data that is typically sent between the master and the slaves is low. It's of the order of a few hundred bytes. So it's essentially just a bunch of doubles, which are the new parameter values. That's pretty much the largest amount of data that is sent in any given step. Now, how well does it work? That depends enormously on what kind of fit you do. So let's first consider for parallelization a very simple example. So you have a single PDF that you fit to an unbinned data set. So these are then n event calculations which are all of the same type. So how well does parallelization performance scale? I just wrote down a few things here to think about and that we also run into. So the CPU time for the fit is then reduced by a factor n CPU because you divide things, and then you have some additional calculations that are inherent to the protocol, and you have some additional calculations that are inherent to the way the split is done. Now the protocol overhead is typically very small when you divide likelihoods, at least from the CPU point of view. It's really just adding back a few components together. The computational overhead that you gain from doing the calculation in n parts, it varies by the situation. For example, in the way it's currently done in RooFit, each of the slaves will calculate separately the normalization integral for the PDF. So if you have an example where this and where this normalization integral is an analytical integral, this is a negligible overhead. So this will be, if you have 1,000 events, it's one evaluation which takes about the same amount of CPU, and you're already talking about per mil levels. If there is a numerical integral, each of those slaves will calculate the numerical integral, and that's a potential serious issue, because if numerical integration takes half of the total CPU time, then clearly parallelization and this strategy is not going to work very well. So this is one of the issues I aim to address, and I will also come back to this. Now, of course, when you talk about parallelization, it's not just about CPU time, but also about wall time, because that's what you aim to minimize. And then there are a few other things that can cause the parallelization not to perform well. So you have additional wall time overhead from the protocol. So this is just wall time spent in the inter-process communication. As it turns out, you can also incur substantial overhead from the scheduling of the other processes. If you send the calculate request out, not all of those processes might start running immediately due to scheduling issues from the operating system. So this generates some level of additional waiting. And finally, there is also additional wall time that you can wait if there is an imbalance between the calculation times of all of the slaves. If all of the slaves take exactly the same time, this is 0, but if it varies a little bit, there will be some waiting time here. In particular, if you run over many CPUs, the calculation times will be short and the variance between those might increase. Now, clearly for protocol wall time overhead, this must be small, otherwise we can't parallelize very well. We've realized that scheduling overhead from the operating system can be quite a problem in reality. If you look at the amount of CPU that is spent in each likelihood calculation, this can be a small number, so there are frequent starts and stops of calculations, so you also can incur quite a bit of overhead here. And the last issue, this imbalance due to wall time overhead, this depends a lot on what you do. For the simple toy model, which is one type of likelihood with many events, this will be almost always not a problem. But if you have one of those 500 dataset Higgs combination workspaces where any dataset can, the same likelihood can contain both kilobyte unbinned events and at the same time, 200 one-bin counting experiments, achieving good balance is very, very difficult. Okay, here are a few plots. So these plots were made by Patrick Bos. So as I mentioned, I forgot to mention, but as I listed on the opening slide, I'm not doing this by myself. This work is supported by a grant that I got from the Dutch National E-Science Center. And one part of this grant is that I get one of the engineers to work for me for of the order of 3 years. And Patrick is the guy that is working for me and has been slowly ramping up and learning RooFit, and has been as a starting project doing some of the timings and the measurements to see what we currently have as a sort of a basis, or to see where we should go next. So what I show you here is a couple of plots which shows you the performance of essentially the easiest possible scenario to parallelize a fit, which is an unbinned maximum likelihood fit, to a PDF, which is a sum of Gaussians. So all of these have analytical normalization. So you'd expect very little overhead just from the way the PDF is structured. So on these plots you see 3 times the same thing. You see the wall time of the fit as function of the number of CPUs that is used. The bottom line in each of these 3 plots is the ideal curve. So this is the amount of wall time that the fit should take under perfect parallelization performance assumptions. And the top plot shows you the actual performance. The difference between the 3 plots, so left is a very short fit, which would take 3 seconds if you run it on one CPU. The middle one has 10 times more data, and the rightmost one has again 10 times more data, and that takes about 400 seconds if you would run it on a single CPU. What you see is that, in particular for very short fits, the overhead is quite large, and you see that parallelization beyond 2 CPUs doesn't make much sense because the wall time really doesn't decrease anymore. So there seems to be a relatively sizable fixed time overhead, which is clearly the most important for short fits and less important for long fits, but we felt this was actually a bit larger than it should be. So we've been looking to see where this is coming from. So on the next slide, we've actually spent quite a bit of time instrumenting all of the various protocols and components to understand where this could be coming from. One thing we learned early on actually is that the overhead from the communication protocol itself, just to communicate the results forth and back, is actually fairly slow. What you see here is plots that show you this communication overhead as part of the, measured in seconds as function of the number of CPUs. And you see that this wall time overhead increases more or less linearly as the amount of work that is needed with the number of CPUs increases linearly. But if you look at the vertical scale, this is roughly of the order of 1 per mil of the total wall time spent in the CPU. So even though this increases linearly as expected, this by far cannot explain the large overhead that was seen. So another investigation we did was into load balancing. Do we actually have differences? If we run 8 processes which each do 1/8 of the data, do we actually observe wall time differences between these machines? We do these tests on otherwise empty machines, of course. It's very difficult to do wall time measurements if there are other users that can introduce all kinds of randomness. So here you see again 3 curves, one for the slowest and one for the fastest process, and you see that all of this actually also gives quite small differences. So also here the load balancing does not seem to be an issue. And finally, we looked into the issues of Linux scheduling, and that turned out to be a quite major effect on the performance. So Patrick actually knew about this, and this is something I would have never imagined, but it turns out that Linux is constantly reassigning these processors to different CPUs, and that introduces some delay when you have to restart these processes when we're ready to do a calculation. One of the things you can do is that you can set CPU affinity in Linux, so that means that every process will be pinned to a designated core on the CPU. And if you do that, you see from the plots that the whole performance improves dramatically. So now you see the same set of curves as you saw on the previous page. And now you see that the top curve, which is the actual measurement, gets to be quite close to the ideal curve for almost all cases, including the leftmost plot, which is really a quite short plot. And you also see that this enormous scatter that we had in there, which was already the average of 100 measurements, is now much, much smaller. So to quantify it, I mean, if you consider the middle plot, I think, if you look at a 400 CPU second fit, which is sort of a reasonable, candidate for parallelization. I mean, this takes a few minutes. You want to parallelize it over 8 cores. The overhead you incur with respect to the ideal for an 8-core parallelization is now of the order of 5%. And that gets better for longer fits. So you can probably improve on this with work and effort, but I consider this to be good enough for now because I don't think this is going to be a limiting issue compared to the other issues that I want to address. So we've decided to stick with this fairly simplistic model of dividing the work over multiple processes for now, and look into some of the other issues that frustrate scaling when you use numerical integrals and likelihoods. I should just mention that from here on, everything that I mention is a work in progress. So these are ideas we're working on, and they don't have concrete results yet, but I just want to show you in which direction we're going. So the first project is distributed calculation of numerical integrals. So this comes back to an issue I mentioned before. The way the parallelization currently works is that, or in fact, the way the likelihood evaluation works is that you first evaluate all the numerical integrals, and barring special circumstances, those are valid for all events in a data set, and then you evaluate all of the PDFs, which usually takes by far the bulk of the time. If you now split such a calculation over 2 processes as shown over here, The gray block actually gets nicely split in two, but the orange line is replicated, so that means you do those integrations twice, but if the orange part is small, you don't care too much about that. On the other hand, if you have numerical integrals in there, especially higher dimensional numerical integrals, the fact that you replicate this orange block rather than you divide the work quickly becomes an issue, because now you see that if you spread this example I show here over 2 or more CPUs, numeric integration becomes dominant and you gain little by parallelization. So the idea is to implement the following idea, that we also want to parallelize the Monte Carlo integrals. So Monte Carlo integrals in principle lend themselves quite well to parallelization, because they're also based on the notion that you sample a parameter space, and sampling parameter space and evaluating PDFs can be quite easily done in a parallel fashion. But if you think about how the code should be structured, then there is more forth and back between the master and the slave. So you first have to know which Monte Carlo integrals you want to treat separately in a parallel fashion. You have to distribute those calculations, calculate the partial results for those integrals, and distribute the combined results with the answers of those integrals back to the slaves that can then calculate the PDFs or all of the events in a parallel fashion. So this requires a couple of places where things need to be changed. So this needs a modified RooMC integrator. This is probably a bit of tricky work, but the advantage is that once you manage to get this going, is it would work transparently for all PDFs. So users that write code never would need to know that more fancy things are happening behind the curtains here. It would just work. So this is one project that needs a modification. The other thing is, this will come back again, the current very simple sort of master-slave architecture needs to be modified to be able to distribute different kinds of tasks. So now, right now it only can distribute the task of calculate one nth of the likelihood, but in this structure it will also have to be able to say, please evaluate 1/n of the following numerical integrals. And finally, there needs to be some threshold to decide if a particular integral is actually worth distributing. If it takes a relatively short time, this may just introduce more overhead than it's worth it. A second project that's also going on in parallel, which shares some of the work, is intelligent balancing of multi-component likelihoods. So if a likelihood consists of many more than one component, and if you look at a typical fit done in Atlas, this is almost always the case, you get load balancing issues. Now, in the simple example I show you here, you don't have it. If you have two likelihoods components which are both of a reasonable size, you can divide each of those over the slaves. And this is also precisely the strategy that RooFit currently follows. Each component is parallelized over all slaves. As long as there is enough events in both L1 and L2, this works well without much overhead. The problem is if you have many, many more of those, and is also the sizes of these likelihoods to become very different. So if you have, say, 100 likelihoods which are all, one event or one Gaussian or one Poisson, and then you have a few fat ones, unbinned likelihoods, and a few binned likelihoods with a few hundred bins. Of course, you can still persist and you just brute force split all of these, but you can't really split a counting experiment. So that one will just get assigned to one of the two or one of the n slaves by some deterministic strategy. But you don't necessarily end up with something where the load balancing works well. We didn't do a comprehensive study yet on how well this works, but I remember that last year I ran some of these crude parallelization strategies on Atlas Higgs combination likelihoods, and what you end up is that you can achieve a factor 2 speed up, but if you then increase n CPU to 6, it will still only be a factor 2 speed up. So scaling is rather poor for these multi-component likelihoods with very different sizes for the components. So what I would like to do as a new strategy for such PDFs is that you need to measure how long each of these likelihood takes, and also take into account whether they're actually splittable or not, and then dynamically come up with some proposal that splits things in an equitable way. The example I show you here is, for example, that these tiny components, L1 through 4, they just get assigned to one of the slave processes, and the big ones you can divide in some way. And in that way, you would end up with a configuration which would be close to balance. And what you want to do is actually you want to keep measuring if this balance is okay, and maybe rebalance a little bit if it was not quite perfect. Okay, so then I just want to come to sort of what the short and medium term plans are. So for both projects, both for the integration project and for the load balancing project, the first step that we need, this is the work in progress now, is that we need to be able to collect and aggregate timing information of all of the components while the fit is running, so numerical integrals and likelihood components. Then for the first project, we need to actually, for the second project, we need to be able to augment the existing scheduler to do these distributed calculations of multi-component likelihoods with arbitrary splits. So rather than saying everything is split 1 over n over all processes, we can separately specify the fraction for each slave and each likelihood so that we can make these balanced distributions. And we need at least the start of a balancing algorithm that divides the work between n slaves intelligently based on this timing information. I think we do this one first because I think this one is easier. This does not require a lot of work. These are all relatively straightforward extensions of existing code. And then step 3A and B is to also implement the parallel execution strategy for the Monte Carlo integrator. This is a bit of tricky work. But I think this can be done. And then once that exists, also the ability to pull out these integrals in advance and schedule them should be integrated into the current scheduler for the parallel execution. This is the short-term plan. So short-term plan is sort of between here and summer, I think. Medium-term, what I want to do next is somewhat more ambitious, and I just want to stop the presentation here to avoid talking too much in detail about too much future plans and not enough results. I think at this point, once we've demonstrated that both of these projects work, or at least one of these 2 projects works, I want to do a complete rewrite of this parallel distribution in infrastructure. So what's there now is actually kind of ugly and approaching the end of its useful lifetime, given the fact that we need all of these new features. But given the fact that we were not really sure how things are going to work out, I first wanted to make a few test runs by just hacking around the existing infrastructure and just see how it works. And once we gain some useful experience with that, we can come up with a new design where we take this current very rigid master-slave structure into a new set of classes that can do these things in a more clean way. And the goal would then be is that the input would be a PDF with certain optimization algorithms, and the output would be a way to distribute the actual calculations in arbitrary ways over n CPUs. And we can take into account the things we've learned in the next few months when we design this. Now, an important next step in this, and that's why I already mentioned this, is I would also like to have multiple, on the longer term, I would like to have multiple back-end implementations for the calculations. We're focusing now on the existing strategy, which is using a multi-core CPU host, single host, to perform all the calculations, but one could easily envision other back-ends. So you could have a multi-host back-end that would use some kind of proof-like infrastructure to use more than one machine to parallelize things. Another obvious and interesting one is a GPU-based backend that would be able to parallelize calculations on GPUs, or one could even, thinking more freely, think about backends that completely re-express a RooFit expression into some other tool, like TensorFlow or something. So this on my part requires a bit of thinking about how best to design this. One could tie the scheduler implementation to a particular back-end structure, so that means you would have one scheduler for this multi-core parallelization and one scheduler for GPU parallelization. Another way we could go about this is to decouple the scheduler and the back-end implementation so that you can also have hybrid calculation strategies. For example, if you have those Higgs likelihoods or some big likelihood with many small components, that the big components would go on the GPU and the small components which can't be parallelized would stay on CPUs. But that's more or less where we are with our thinking now. I didn't make a conclusion slide, but I think what I said is hopefully clear enough. Thank you.
Thanks very much, Wouter. I think that was very clear. Maybe we can start with questions from outside. So there's quite a few more people outside. Or comments, anything?
Wouter, this is Mike Sokoloff. Hi. So, one of the questions running on CPUs is, as the new architectures are emerging, a lot of them support vectorization. And vectorization seems to provide benefits for other types of activities if you optimize your data structures and at least allow the compiler to do the vectorization for you, and then of course you can rewrite things to do it yourself. Have you been thinking about how to do that optimally on a CPU?
Yeah, I have some ideas for that, but I didn't include them in this presentation. But it should be relatively straightforward to reorganize the order of all the calculations for a RooFit likelihood in such a form that vectorization becomes easy. It's a little bit hard to explain it in detail without some graphs and slides, but the idea is that instead of calculating the likelihood for each event and then go event by event, you can completely reorder things so that you go through every step of the graph. So if you would have, say, a sum of a Gaussian and a uniform, that you would first do all the uniform calculations, then all the Gaussian calculations, and then the summations of all of these. So I should be able to, once the level 2 optimization is completely functional, roll out the reorganization of the calculation of any PDF of arbitrary complexity and such a reordering. And then I think you have a starting point where a backend that could then vectorize those calculations, which are all of the same type, shouldn't be too hard.
No, the concept sounds right. Once it's working, I would love to look at it.
No, I think so. I mean, I think it's all, the next big step really hinges a little bit on getting this new scheduler back-end implementation thing going. So that's why I want to do that first. Once that is realized, and the time scale for that is this year, then we're in a situation where it becomes easy to test other things and to also deploy these kind of strategies.
Yeah. So the somewhat related question is whether you've tested this scaling on the new Xeon Phi systems, and in particular, and this is something both for other systems as well, but when you when you change the number of threads from the number of physical, or you change the number of cores from the number of physical cores to the number of logical cores with hyperthreading, whatever, what the scaling looks like, because the Xeon Phi is supposed to gain a lot of its benefit by being able to run 4 threads on each of the physical cores. And I'm just wondering if you know how the scaling changes when you go up to the number of physical cores, and then you go from the number of physical cores to the number of logical cores.
We haven't looked into that, but it's relatively straightforward to do for us. I mean, all the scripts we have to make all these tests, we've saved everything. So I don't know off the top of my head which architecture we use to run these tests. I'm trying to look it up now, but there's a good chance that this will take me more than 30 seconds. Wait a second. Let's see. So the machine I tested it on, say, is Intel Xeon CPU E5 2450. Is that a Xeon 5?
No, I said, I'm sorry, Xeon 5, the new, what's the other name?
5.
Like the Ninjas with the 64 physical cores.
No,
they run more
sorry,
slowly.
I misunderstood your question. No, we haven't, but if we can have access to one of those machines, it's completely easy for us to do those tests.
I can give you access to one that's trivial.
Oh, that's great. No, yes, we would like that.
Okay, I'll get back to you on that.
Thanks.
Right, any questions from our side maybe before we can start? There's not any questions from Sven?
Yes. Yeah, it turns out that I have two simple questions on the implementation side, just out of curiosity, because I implemented something in the multiprocess regime before. But for example, I didn't know about the CPU affinity thing. So the first question is that something that it can be set, like using CPU affinity or not? Is that something that can be set on the RooFit side, or is it a system-wide configuration?
Yeah, I agree with you. I think that's a good idea to just do the
So we have a test version of RooFit which can call this so I mean can configure it for you. So I mean most Linux machines seem to be configured in such a way that user processors are allowed to do this. But for example, Macs by default are not. But when we have code that we can insert in RooFit that allows you to configure it on a Linux machine so that it does this.
That's right.
Okay, thank you. And the other thing, even more technical, maybe. Sorry about these not very interesting questions, but you mentioned that you're using a system of pipes, Linux pipes and shared memory to do inter-process communication. And I was curious as which technology this is, if it has a name, if it is a RooFit class, or is it an external library that you're using? What is it?
It's a separate RooFit class, which was written by Manuel Schiller, who worked on LHCP and contributed this. So it's called RooFit Bidirectional Memory Mapped Pipe, or something like that. If you start browsing around the code, you will recognize that very long class name. So it's a standalone class, which to the outside looks very much like a regular pipe, but then internally has a smarter mechanism to move data from one process to another.
All right. Thank you very much.
You're welcome.
Very nice presentation.
Thanks.
I have maybe a question on the Monte Carlo integration. Do you think many people using Monte Carlo integration, or the majority maybe use the adaptive one in multi-dimension, especially for integrals of 2 or 3 dimensions? Because Monte Carlo integration suffers more problems like of precision, and you need, especially for min-width, you can suffer from problem of precision when you're doing minimization.
I think many people use the adaptive one, but sometimes you're stuck with these, 4 or 5 dimensional ones where also adaptive is not so great anymore. Parallelizing adaptive, I think, is kind of a horrible problem, having looked at the code. It's not easy at all. I think only the Monte Carlo integrator provides an easy path to parallelization.
But anyway, you're looking at the way of, if you parallelize the way of splitting the likelihood. So if you have many different channels, you can parallelize the integration on the different layers.
Yeah, so I think that's another way these things help each other, right? Because if you have many components in a fit, and each of those components have heavy numerical integrals, you also gain by if you could organize the work in such a way that every slave does one data set, then you're already there. That's also the reason that we want to do that part of the project first. That seems easier, and it might also help with numeric integration.
Yeah, that makes sense. Thank you.
Hi, Wouter, this is Kyle. I was curious have you thought about, in terms of the sort of computational graph and this kind of longer term discussion we've had about sort of separating the modeling side and from an actual execution engine of it? Have you thought at all about kind of like a schema or anything for like representing that computational graph?
No, not yet. So I think, as I mentioned on the last slide, this is a little bit in progress, this work. So I first wanted to have the concrete organization of this new scheduler class implemented for the current parallelization strategy. And usually when you do such projects, you learn quite a few things about what's a good interface by at least having tried it once. And once we have that one implementation running, I think then the next logical step is to see how we can abstract that further. As I mentioned also in the last slide, one of the issues where I'm a little bit undecided is whether schedulers and backends are the same thing or they should remain separate things. That's a large part of the open question still that influences all of this.
Okay, and can you say just a little bit more about, in terms of this kind of load balancing problem that you were saying you didn't think would take too long? Can you just say a little bit more of a...
Well, I mean, if you think about in terms of Higgs physics PDFs, I mean, you end up with these things that have like 300 subsidiary measurements, which are all totally trivial, simple things, and then you have 5 or 6 big chunks.
Right. No, I mean, I get the point of what you want to do, but in
Yeah.
terms of the work that needs to be done, and if we can
Well,
be helpful.
What needs to be done is relatively straightforward. We need a tool, we need infrastructure to time how long all of the components take. So this is what we're currently setting up. And then once you have all that timing information, we need a simple strategy to assign PDFs whole or partially to slaves, rather than just assigning one nth of every PDF to every slave.
Mm-hmm. Okay, but I mean, you're setting up the timing. I mean, if you wanted help there, it would be on which side, or you don't need help there?
Well, Patrick is currently. I mean, I expect to have. I mean, it's almost working. I mean, we just had some technical mishap showing timing numbers for this week, but the timing is nearly there. So, yeah. So that's. I think that's largely under control. We were talking to Vince this afternoon because Vince offered to also have some time to help us out and things. So we were thinking of having Vince starting on the algorithm to do the distribution over the processes in parallel, so that we can then put those things together in 1 or 2 weeks.
Okay. Okay. And can I ask one more question? In terms of the memory footprint, like for the big fits, sometimes like trying to run on multiple CPUs, the problems we have are that we, at least certainly with the fork strategy, you run out of memory. But have you, sorry, most of this, I'm just looking back at the slide, it seems like most of it's about kind of the CPU side of it, but where does the kind of being able to have like a totally different process, potentially on a different machine, and communicating through this this kind of API that you have, where does that fit in this schedule?
Well, yeah, memory is a separate issue. It's not as, I mean, in principle, if you would use multi-threading rather than multi-process, you could save on memory. On the other hand, Unix typically has some copy on write strategy for actual memory pages. So that means that in practice, if you look at the real memory use, only the memory pages to which you write, they get duplicated when you do a fork. So, I mean, it's not if you do fork 8 processes that the total memory, the actual memory footprint increases by a factor of 8. So we have to see how much you can gain by switching to multi-threading, but it may not be as much as you think.
Okay. Great. Thank you.
Good? If there's nothing else, then thanks again, Wouter. And we should probably move to the second presentation to avoid having a very long meeting. I realize it's not super early in the day. Thanks, Ken. Okay, Gary, I have the slides here. Okay.
Would you like me to share my screen, or should we do it from there?
Or you can just share it again if it's fine. It worked perfectly fine, so if you want to share it to me, then you have full control. Just try it. Yeah, you see that? Get it here. Yeah, please go ahead. Thanks.
Okay. All right, so I'm going to be talking about the CLI 11, which is a command line parsing library that I wrote in conjunction with some work that I was doing on the GooFit fitting library. So the origin of this library is that a lot of the analysis code in GooFit consists mostly of two things. You either have a PDF, which you have to write in the GooFit form in sort of a CUDA OpenMP mix, and model code. And GooFit really tries to make the model code as simple as possible, giving it a RooFit-like look and behavior. But a lot of this code in the examples and in some of the analyses that I looked at was really just setting up command line parsing. Or worse, it had a lot of hard-coded values and you had to recompile everything each time. And there were lots of separate files sitting around. This provided a lot of the seg faults and examples if you just didn't set up the options just right. So I looked at providing a way in GooFit to do this parsing. So the requirements for this sort of a command line parser is that it needs to be very simple and easy to use. It should provide plain types, so ints, floats, doubles, those sorts of things with no runtime lookup. You shouldn't be looking this up out of a dictionary because you might need to use this in performant code. It should be very easy to include. It should ideally be part of GooFit or be something it could get very easily as a library. It should support the standard shell idiom so that it's natural to work with your GooFit program. It would work a lot like Git or other standard command line tools. It should provide support for subcommands. In GooFit, you're often setting up models and you need to have, say, a toy fit, or you might have a variety of different things that completely change the behavior of the program. So subcommands was an important feature that was needed. I'll go into what those are in a little bit. It needed to be able to support configuration files, because if you have 30 or 40 parameters in your model, you probably don't want to enter all of them in the command line, or maybe set them all to a default, but have a configuration file that you could input instead of command line. And ideally, whatever this tool would be, whatever this library would be, it would be extendable and customizable by a toolkit such as GooFit. So there are some other libraries out there for parsing program options. Probably the most famous one is the Boost Program Options library. It's sort of the classic parser. The issues are those: it provides a really large dependency for a library. You have to include Boost as a dependency, which is something GooFit currently does not do. And even if you have Boost as a dependency, you have to actually compile the program options portion of it. So even just getting the headers for Boost or getting a standard download of it might not be enough. It has a very peculiar syntax, and it's hard to exit your program cleanly, especially if you want to do things like unwind the stack and make sure your open files get closed and things like that. However, this actually started out as a wrapper to the Boost Program Options library, and I used this in a previous. So the previous incarnation of this was something I used a few years ago, and it was born out of that sort of idea. There are a few others. There are more. There's a list of all the major command line options libraries that I know of on the main web page, but a couple of the ones that I've seen used are tclap, which really just is not very well supported anymore, and has a syntax I don't really consider ideal, and gflags, which is Google's attempt, which doesn't have subcommands and is built out of macros, which allows it to have a fairly nice syntax, but it's not really ideal to be doing this all in macros.
I can make a quick comment. Have you tried
Sure.
the getOp function from Unix?
Yes, that's still not necessarily ideal. Especially if you're going to do something like subcommands, which it really does not support, and that's fairly limited.
Mm-hmm.
So this is a much more powerful system, and I try to stay compatible with the sort of the getOp style as far as the actual command line goes. Okay. So this library is designed to mimic the excellent plumbum.cli library, which I'm a maintainer on. but is native to C++ 11s. So the basic structure is different, but a lot of the terminology is the same. After starting this, I expanded to include some other features that I thought might be useful from other libraries, such as the click, which is plumbum.cli's main competitor, if you're going to call it that. It's a header-only library. It compiles itself into a single header file if you want to simply drop the header file in. It only depends on C++ 11, and it does not require the regex model module, which allows it to work on GCC 4.7 and above. And you can use this, the tool standalone, or you can subclass them for a toolkit, such as GooFit. It has a thorough set of testing that's provided. The continuous integration runs on Linux, Mac, and Windows. The compilers that you see listed here are all tested. It has 100% test coverage on codecov.io, and that's automatically populated after each test run. And the online build also creates the single header file version on releases, and it produces the API documentation, which is a doxygen system, and every function, method, and member is documented. So here's a quick example of what command line parsing looks like. You have your program. You have the value 1 here, which would be a positional, because it doesn't have a name. The -v is a short flag. The z is a chained short flag. So you could also say -v-z. The -f is a option, and that takes a value, so then the remaining part is the value. You can optionally put a space in here. This is one of the things that makes command line parsing a little bit tricky, because the chained options, the parser has to know beforehand what those options are, whether they're flags or options, to know what that means, to know that z is a flag and not just an argument to the -v option. If you've used the tar command in Linux, you'll be used to this, because that's the sort of standard commands that you give that are generally a mixture of flags and options. And there's also a long option, which is started by a double dash, and then all the letters afterwards are the name of the option. And that can be followed by an equal sign or by a space. Okay. Here's another example. This is a subcommand. If you use git, you'll notice that the checkout is a subcommand. -q, which it should say -q is a short flag, not -in. -q is a short flag, and that goes to checkout, not to get. The -- is a positional separator. That means everything afterwards is a positional, even if it starts with a dash or a double dash. So that's what command line parsing looks like. The parser looks like this. You create a application, and you can give it an optional description. Then you add your options. I'll show you how that's done. And then the 4 lines are the ones that are recommended for doing the actual parsing. This will correctly do the parsing. It will allow you to give the correct error code, and it will unwind your stack. And this is expected to be in your main function, obviously by the return statements. You can just call app.parse. It'll throw an error, and if you don't catch it, that will end your program, but your stack won't be unwound, so you may have some issues with files being left open and things like that. Okay. If you add a flag like this, you can give it a short name or a long name or both, or as many names as you wish. You then give it a variable that it's going to take a reference to. This could be either a int-like or a bool. And then you can give it an optional help string. It uses the C++ idiom of SFINAE. Substitution failure is not an error. To select the behavior, so you can use any int-like here. You could do an unsigned int or a char or whatever you'd like, and it will pick the correct behavior. Or you can use a bool. If you use a bool, you can only give one of these on the command line. If you use an int-like, then it will give you the number of times that flag was passed as the value that it puts inside output. This is adding an option. You can simply set up a value. It supports 6 different types of values: an int-like, a float-like, a string-like, and then it can also take a vector of any of those 3. It correctly selects the behavior based on the value that you give. And because it's using this templated approach, you can do T-strings or boost file system or anything you'd like here, as long as it behaves like a string, as long as it takes assignment from a string. So,
sorry.
What?
What is the syntax for a vector when you pass a vector option, a vector of int, let's say?
It's you just do a vector of int output, and then you give that in. Same syntax.
No, I mean when I'm calling the program, how do I pass a vector?
As a command line option.
So by default, it will take all of the arguments until your next named argument, but you can control that, and I'll show you that in about a page. Unfortunately, I won't have an example of passing a vector, but there's examples in the library. But you would say, for example, if it was dash dash vector, you would just say dash dash vector 1 space 2 space 3, and that would be a 3-value vector. You can also give the option multiple times. You could do dash dash vector 1, dash dash vector 2, dash dash vector 3, and that would also fill the vector. You can also give any arbitrary transformation function. That's actually how all of these are built. The options themselves are not templated. It's done entirely through Lambda functions. So that greatly simplifies the several of the features of the library, because it's actually storing a single class. It's not storing a templated class. There's also an optional value after the help string. You can also optionally give it the value true, which will tell it to capture the default value. It does not capture that by default because there's no requirement that this value be initialized or even a printable value at all. It simply needs to be able to understand how to convert from a string, not to a string. Okay. And in this case, if you don't give a dash in front of the name, that's a positional. You can only give one positional name, but you can combine that with short and long names if you'd like. There are several specialty functions as well. You can do an add set, which allows you to pick from a set, and that way if a value has to be one of 3 things, like 3 different decay chains or something like that, then it will error if it's not in that. It's not a member of that set, and that supports the ints, floats, or strings. There's a special version for add complex, which allows you to add a complex number, and that will support any complex-like number, like a boost complex or standard complex. And there's a add config, which allows you to add a option for a configuration file. Now these options, these adds that you've seen, return pointers. So those pointers actually let you modify the behavior of that option. And then if you keep a reference to that pointer, you can also count the number of times that option was passed. For example, if it's you don't have a reasonable default value and you don't want to make it required, then you can count to see if it's been given on the command line or not. So here's a slightly more advanced example. This is adding a T-string for file name, and this one is making it a required option, and it's checking to see if it's an existing file through a validator, which I'll mention in just a second. So this is how you configure it. You often do not need to store a pointer to an option or even know that it exists. You can often just chain the configuration like this. These are the different modifiers that are provided. You can make it a required option. If it's a vector, you can tell it to expect a certain number. So if you require, say, a 3 vector, you can require that it have a length of 3. If you leave this default, if you don't put this on, it just will keep going until either the command ends or until it sees another short option. You can also set required or excluded options. This is from plumbum.cli, and you can require that one option can require that another option be passed, or can require that another option not be passed. And this is variadic. You can add as many as you'd like, or you can chain a series of these. You can also take input from an environment variable. You can group these into categories. Now, if the grouping is only for help, it doesn't actually modify anything but the help string that's generated. You can tell it to be case insensitive, and then there are these validators. So if you do check, then you can just take any function that returns a true false. It takes a string and turns a true false, and that can validate something about your command line option. So existing file, existing directory, non-existent path, and then inside of a range from a lower to an upper bound. These were also inspired by the plumbum.cli methods. This already reduced a lot of errors with files not existing or files existing, and root simply continuing on and reporting 0 events instead of giving you a nice error. So subcommands are added in this way, app.add subcommand, and then you give it a name and an optional help string, and it produces a standard CLI app. Now this is there's no difference between this and your main app. So you can add a subcommand to a subcommand if you like. It has all the same features. You can add anything you want to it. You can chain these infinitely. You could have a series of subcommands if you wanted to. So there's really not much else to add for subcommands. They're just new apps. Now you do get a pointer to it, so you will be using the arrow after subcom instead of a dot. If you want to, you can just use standard C syntax to take a reference to that instead of taking a pointer. But I'll just be using a pointer because that's the way options work. So these are the different modifiers that are available for commands or subcommands. You can make them also ignore case, and they'll inherit the parent, so you can just do app.ignore case, and then all your subcommands will be case insensitive. This is very useful if you happen to be doing pkpi and you can't remember whether you made k capital or not. That's actually why that's there. There's a feature called fall through, which I haven't seen listed in other libraries, but it actually turns out to be quite useful if these things are mapping to a physics model. Because what fall through does is it lets an option, if an option is passed to a subcommand on the command line, and that subcommand does not have that option, it will simply let it fall through to the parent, and then the parent will check and see if it has that option. So you can set shared options on your parent, and then you can set the unique options on the children, and then it doesn't matter where they're passed on the command line. You can just immediately put your subcommand and then list all your shared and your unique options. So shared masses, widths, things like that. You can require that a subcommand be passed. You can require that a certain number of subcommands be passed. This was from the Click library. They had some techniques for subcommand chaining that needed this. You can set a callback function, which I'll mention in just a second. You can allow extras. This really only makes sense on your main command, and this allows the extra arguments, extra unrecognized arguments, to simply be returned from parse instead of causing an error. This was added primarily to let this be a little bit more similar to a T application. I will go over near the end. And you can also get a list of subcommands that were parsed. So there are 3 ways to use these subcommands. You can just take these pointers that you have and just check to see if they were parsed. You can run over the list of the ones that it received on the command line from .get subcommands. Or possibly the easiest way, if you're comfortable with C++11, is to simply set callbacks. And if you set a callback and you capture by reference, CLI11 will simply do the right thing. It will go ahead and parse all of the options for you, and then all of your option values will be valid inside the callback, which is kind of a neat trick. So this allows you to simply write the code that you would be running for each subcommand in the subcommand definition itself. So the best method depends on your particular application. The set callback is what's used primarily in the GoofIt examples. It also supports configuration, and these are through INI files. This was inspired by the Boost program options. You can set values inside subcommands. All the standard features of INI files are supported, such as comments, like you see at the top, that start with a semicolon. I have no idea why INI files start with comments with semicolons, but it supports that. And you can also use section headers. And default is the section header for your main command. This all mixes in with the command line. You can set value. You can override values on the command line that are in your INI file. You can actually produce INI files. So if you want to record inside a log file exactly what options this particular run ran with, you can do that. It can produce the INI file string that it would have received. And flags and subcommands, things like that, are all supported. And as I mentioned earlier, you can also read in from environment variables. One of the strong points of CLI 11 is that it can integrate very nicely into a library. So the main app can be subclassed, and you can modify the way that that behaves. And there are several hooks that are provided so that you can modify behaviors inside the main sequences. So in GoofIt, this is how it is implemented in GoofIt. There's a GoofIt application, and that adds some custom options so that you can pick which GPU you want to use, or you can print out information about which GPU you're using in your system, which automatically get added to all GoofIt applications. This is also used to add a spot for the MPI setup and teardown for when MPI support was added to GoofIt. And this provides a sort of a T application style constructor and run. So in GoofIt, you add the arguments to the constructor, and then you call the run instead of parse. So it looks much more like a T application. And the GoofIt supports nice color output through the Rang library, and that nicely integrates in with this system. So here's an example of what it looks like to print out the help from one of these commands. This is for the pi0 fit in GoofIt, a slightly older version, but I think all the features are the same. And I'm running inside a Docker container there, so ignore the first line. So it prints out the help message. It shows you what the usage that's generated from the behavior, and then it lists the subcommands and their help, as well as the main options, the shared options. And then if you were to try checking the help on for example, the canonical subcommand, then that shows you the different options that are generated there. They have defaults. You'll see a set near the bottom where you pick between histogram, parameter, or sideband. And all these things give you nice errors if, for example, you select a model that doesn't exist, or if you try to give a float to an int or something like that. Not all of these have descriptions, unfortunately, but it still supports those and prints nicely. Okay. So the status of the library, it's nearing a 1.0 release. The 0.9 release was released yesterday, and that actually is the 9th release. The API has been stable for the last several versions. The last few have been mostly focused on final polish. Really the only tasks that remain are to evaluate user feedback and to evaluate compatibility with Root 6 or 7. And I want to try to implement a version of this that integrates with T application and simply allows T application to gain these extra parsing options. And if that works, if I'm able to get that to work, I might see if anyone's interested in including that in Root. The GoofIt 2.0 release will be preceded by the official stable release of CLI 11. So there are 3 different ways to get it. You can download the all-in-one header file from the latest release page on GitHub. You can just download the Git repository, hopefully as a submodule of whatever project you're working on. Or you can use the add.cli.cmake tool, which will automatically download it and provide it in a CMake build system. Feel free to look at the other CMake tools that are in the CLI utils CMake repository as well. The findroot.cmake is a very nice version of findroot that provides a lot of CMake 3 features. Feel free to get involved. You can open an issue or pull request or chat on Gitter. If you try this out, and you should be able to just use it with any system, including RooFit, directly, though it is a little nicer if it's fully integrated. But you can actually try this out today if you'd like.
Thank you much, Henry. Okay, so maybe for change and start with any questions or comments from the student side.
So this is Mike. Let me ask you a leading question, Henry.
Yes.
Are you available to consult individually with anyone who wants to try this out?
Yes. Feel free to contact me directly or through the Gitter link, which is some sort of a chat system that's tied to GitHub. So yes, I am available.
I think there was a question here or comment? No, oh sorry, here already.
Can I?
Go ahead.
Can I ask a question?
Yeah, go.
Do you have plans to include this in Root itself, so that this will be available kind of by default? I mean, one problem with having libraries like this is that it makes sort of having it makes integration of if you include use of this of the library CLI 11 in say some random program, then you also have to include instructions to download the CLI 11 or include the code or within another library, and then you get incompatibilities. So I'm just wondering if it could be very useful to have it as part of standard root, obviously when you've got it a stable version.
Yes, that is the idea. One of the reasons I developed it to be very general, not tied to GoofIt in any way. So I want to try my hand at actually putting this into root, see if I can integrate it into T application, and then suggest it as something that could be included directly in root and it would just be available. For a lot of root scripts, this would be very, very useful, because you may create a T application, but with T application you can't add any extra parsing. You're stuck with just the options that it has, which are useful, batch processing, a few of the options it adds. But you have to parse the rest yourself. But I don't have a working implementation of that. And there are a couple of things about the T application that make it a little bit tricky. The T application does its parsing at sort of the beginning when you create the T application, which is a little peculiar. Otherwise, this might be a potential inclusion in Root 7. But yeah, I'd like to talk with people about this. Hmm?
Sorry, I was just going to say another use case, which I've often come across, is where you have fairly short, not for a full application, but where you have fairly short C++ would be called scripts that are actually just a .cxx file or something, which is run from the root command line. And if somehow this could be integrated into the root startup, so that you can then apply options to those scripts, that would be much better than the current scheme, which where you have to, or is an alternative to the current scheme where you have to put command line options in brackets and and you have, I don't know if you've done this, but you have kind of 15 options where half of them are defaulted, and it becomes horrible to actually use.
Yeah, and it tends to require quotes in peculiar places. So I remember a series of quotes and brackets. Yes, I've done that.
So if this could be incorporated into the way that root starts up, it could make that sort of scripting become much more like the way you would do it in Python, for example. And is one of the reasons. Okay, maybe people who maybe keeping C++ difficult to use is a way to push people to using Python, but it would be nice to make C++ as easy to use as Python for those that want to.
Yes, I had not really thought about the about that. That should be possible. I'll have to look into that. So I've mostly been thinking about T application. I haven't really thought about the interaction with scripts, but that might be possible too.
Probably need some discussion with the root maintainers, because that obviously would fit. Isn't something you can just add on to the top of root, but would need somehow integrating into the root startup. But I think, at least for me and the way that I use root, that would be an enormous improvement in the usability of root. And sort of you've done most of the hard work here by making an easy-to-use command line parsing.
I'll actually need to talk to the root team to see how that's. I'm not very familiar with how that system runs. I looked at T application and how it's implemented, but I would probably need to talk to somebody about how that's implemented to see if it would be possible. And I would assume yes, but it would require some deep changes to root or additions to root. Okay.
Maybe both of you should talk offline about a specific example. It seems like, I don't recognize the voice, but it seems like the person who's speaking has some very concrete examples. Probably best to show it to Henry.
Okay, that would be helpful, I think. I've done this before too, but it would be nice just to have like an example command line that I could demonstrate would be easier.
Okay. Any other questions or comments here? If nothing else, then we close this meeting. Thank you again, everybody, for coming and for presenting as well. And see you in the next meeting then. Bye-bye.
Bye-bye.
Bye.
Bye, thanks.